Hi everyone, this is the Hungry Math Professor here, and well, thank you for coming to my channel. And you might notice I'm wearing a much more casual garb this time, but I'm keeping it blue. For those of you who don't know the Hungry Math Professor in person, the summers are extremely sweaty for me, and so I'm going to keep it in this t-shirt for now. But today I want to record a review of this book called An Invitation to Model Theory by Jonathan Kirby. And I really like this book. I used it with an undergraduate student doing an independent study where we're going to do some expository research comparing real closed fields versus complete order fields as a way of comparing first order logic versus second order logic. And for those of you who are not familiar with the differences between first order and second order logic, I won't discuss that here, but I've already recorded a video where I discuss this. And so I'll link to that video in the description for those who want to go a little bit deeper. And this book is particularly good for self-study, in my opinion, because it's very well written and it's broken up into small chapters, small chunks. And at the end of every chapter, there are a lot of good exercises which help to make sure you understood what you read. So I think this is really well written for self-study. And it's also quite unique in the fact that it's written specifically for an undergraduate audience, which is quite unusual for model theory. Usually, model theory isn't studied until graduate school and really is only studied by those who wind up going into mathematical logic. It's not a topic that is sort of in the traditional canon of undergraduate studies or even graduate studies. So you really have to be interested in logic and interested in going into model theory. And since it's an undergraduate textbook on model theory, one of the choices that the author made, which I think is a good choice, is to basically take set theory for granted and not get into the technical weeds of how set theory is defined. And so from the very beginning, it's assuming that you can just basically work with set theory as a place where you can build mathematical structures. Um, and so, this is designed to be an undergraduate textbook. If you were to take model theory in grad school, you'd have to go back from scratch and learn first order logic very, very carefully, and then discuss set theory in first order logic, and then discuss model theory for set theory, and then just discuss model theory inside of Zermelo-Fraenkel's set theory. But this is a typical, I think, thing that we do in undergraduate curriculums in general. You study analysis and abstract algebra and various other topics as an undergraduate, but then when you go to grad school, you relearn abstract algebra analysis, but you do it at a much quicker pace, at a much more technical level, and so in a much more in-depth level. And so this is a typical thing. I think this is a good move that the author made. You don't want to get into all the technicalities of set theory for an undergraduate student, but you want to give them some really interesting ideas from model theory, exposure to model theory, and if they're interested, they can continue to study later on in grad school if they pursue that. So I think this is a good move on Kirby's part. So let me try to give you just a basic idea of what model theory is all about. Okay, so for one, you're going to use the language of first order logic to express axioms, right? Axioms are properties that you want to study of mathematical objects. So a lot of these properties can be the kind of things you're used to from studying algebra at some point in your mathematical career. So you may want to study a addition, which is commutative, right, or associative, or you want two operations, addition and multiplication. You want them to be distributive over each other. So these kinds of properties of like the commutativity or associativity or distributive property can be expressed in first order logic as axioms. So you're going to pick a certain number of axioms that you want to study, and then model theory asks, what are the models of these axioms? So what do I mean by that? Like, what is an example of a mathematical structure which satisfies the axioms that you chose? So, for example, the real numbers satisfy commutativity of addition and commutativity of multiplication, and addition and multiplication distribute over each other. So The real numbers are an example of what we call a field, where you have basically all the algebraic properties that you're used to from studying algebra in high school. And the real numbers also come with an ordering, so it has a less than or equal to sign, and that ordering is respects addition and multiplication. You can see how all these axioms are written down carefully, but the point is that we call the real numbers an example of what's called an ordered field. Okay, great. So let's say you're talking about ordered fields. You have all the nice algebraic properties they're used to, and you have a less than or equal to sign, and you have the less than or equal sign respects these algebraic properties in a certain way. That's what we talk about ordered fields. Then model theory asks to look at sort of study all the different models, all the different examples of mathematical structures that satisfy those axioms, and then looks for relationships between these models and tries to establish properties about these models. And so that's what, just a general description of what model theory is all about. To give you just one sort of interesting result from model theory. I mean, one interesting result is the compactness theorem. I won't talk about that here because that is more technical, but you may want to check that out if you're interested. But something else that I want to mention is, for instance, one thing you might want to do with an axiom system is to completely characterize a particular mathematical structure. So in particular, let's talk about the real numbers, right? An informal way of thinking about that is just the set of all decimals. But there's, of course, a more formal way of doing that. But let's say you want to come up with a system of axioms in first order logic, which completely characterize the real numbers. Okay, so they are an ordered field. But that alone will not characterize the real numbers because the rational numbers are also an ordered field, and the rational numbers are not the real numbers. So you have to add some more axioms, right? And anyway, oftentimes one will add axioms requiring certain roots of certain algebraic polynomials, or you may want to try to add completeness types axioms, which are tricky to do in first order logic. But let me just say that, like, no matter what axioms you add, there's a theorem of model theory there's two of them, but you can think about them as one, called the upward and downward Lowenheim-Skolem theorem. And what they tell you is that no matter what axiom system you pick to try to characterize the real numbers, there will always be other models of different sizes of infinity. So what that means is that you cannot completely characterize the real numbers up to isomorphism, meaning that there may be many different models but they're all isomorphic is not going to be possible in model theory. Instead, there will always be models of any axiom system you choose to pick for the real numbers of any different size of infinity. So in particular, no matter what axioms you pick to describe the real numbers, there will always be a countable model of that system of axioms. That's the downward Lowenheim-Skolem theorem. But the upward Lowenheim-Skolem theorem says there will always be a model of every size of infinity larger than the real numbers as well. So there'll be models of every size of infinity, and there could be many different models that are not isomorphic to each other. And this is just a fact of first order logic that one has to grapple with, and that you can't sort of characterize the real numbers or characterize really any mathematical object you want completely in this, without there being different models of different cardinality. That being said, there's different notions of saying, the source of one you could say is that two models are isomorphic. That's like the strongest notion of two models being the same. But if models are different cardinality, they definitely cannot be isomorphic. But there are other notions of two models being equivalent, maybe not exactly isomorphic, but other ways of talking about them being equivalent, which is an important thing to study in model theory, such as one can ask that any statement which is true in one model is also true in another model, which is like a very important notion of equivalence in first order logic and model theory. So that's just to give you a little taste of the kind of things you can study in model theory. There's many more interesting theorems and results and examples to think about, a lot of them that are covered in this book. And I really encourage you, if you're interested in just kind of getting your feet wet in model theory and first order logic, and you're looking for a text which is not too technical, a way to try to just kind of get into it, then I highly recommend this book. And so thank you for checking out this video. Please like, comment, and subscribe, and let me know what you think if you take a look at this book.